Reviewing a little bit from last time, the cell potential. We have our redox reaction at the top here with zinc solid reacting with copper 2 ion, producing the zinc ion and the copper solid, as you see up here. The cell potential of the oxidation reaction added to the standard reduction potential for, obviously, the reduction. And you have a table that you look these values up on. Everything on the table, though, is written as a reduction half reaction. That's called standard reduction potentials. So you have to look at your reaction, the overall reaction, and figure out which one's being oxidized. Once you figure out which one's being oxidized, you look up that particular reaction on the standard reduction potential table, and you flip it. And when you flip the reaction to make it being oxidized rather than being reduced, you change the sign on the voltage, that value. So if I were to look it up, you do have the table on the back of your notes. This table on the back of your notes is arranged by the actual potential numbers themselves. So it starts with the highest reduction potential of fluorine being reduced, which is a positive 2.87. And then the table lists the different reactions in order of their standard reduction potential, all the way to the bottom on the right-hand side where lithium being reduced is a negative 3.05. So we flip that one. If we want lithium to be oxidized, and it becomes a positive 3.05. So this one on your notes is arranged by the actual reduction potential values themselves. In your textbook, in Appendix E, it shows you the standard reduction potentials, but it arranges them alphabetically based off of the elements involved. So there's good points to that because it's easier to find your elements. But arranging it by the voltage and the standard reduction potential also has a little bit of a benefit in being able to decide what's going to react spontaneously. So if I'm looking at this example up here, we can see that zinc is the one being oxidized and the copper is being reduced. If I go up here and I look for my copper 1, the copper plus 2 going to copper metal, that has a standard reduction potential, or an E-red. This one's, looking on the chart, is 0.34 voltage. That's a positive value. I look up here too to find the zinc one. And the zinc is written as it's being reduced, so zinc plus 2 electrons gives you zinc metal. But we're going to take that and flip it. So on here, it's being shown as an E-red that equals negative 0.076 for the zinc. But remember, we're going to flip it, so it's going to end up becoming deoxidation that ends up being a positive 0.76 because we flipped the reaction. And therefore, now we could calculate our overall E cell for both reactions together. And that would be 0.34 for this one, 0.76 now for this one. And that gives us an overall value of 1.10 voltage. And that is one of the criteria for it to be a galvanic cell or a voltaic cell. It has to have a positive overall E cell potential in order to run spontaneously. If you have a negative one, it is not going to run, and therefore galvanic cells and voltaic cells have to be able to run spontaneously, so it wouldn't fit that definition. So in this particular one, write a balanced cell reaction and calculate E cell, or the standard potential for this galvanic cell. Do you remember too that the little degree symbol up here, that little degree symbol means what? Standard. So we're looking at If we have gases, they're at 1 atmosphere. Solutions are all at 1 molar, and we're at 298 Kelvin or 25 degrees Celsius. So here, looking at my overall, I can kind of figure out what's being oxidized and what's being reduced. What's being oxidized? Magnesium is being oxidized. It's going from Mg to Mg2+, right? And our chromium is being reduced, going from +3 to +2. So, one of my jobs is to balance this. So, in order to go from Mg to Mg2+, what do I need to add there? That's 2 electrons, good. And for this one, the chromium one, what do I need to add there? 1 electron over here. All right, and in order to balance this, I need to multiply the chromium side by 2 to balance those electrons. Very good. So I would get 2e and now we can merge our equations because we can cancel our electrons. And we end up with 2Cr3 plus Q plus Mg solid, giving us 2Cr2 plus, that's AQ, and Mg2 plus AQ. That's one part of it, balancing the overall reaction. The next part is looking up on the table to find our values. So, for our magnesium 1, we're really looking for magnesium as a reduction. So it would be reverse, it would be Mg2 plus the 2 electrons gives you Mg solid. So if we find that one on our list here, what is its value? 2.37. Is that after you flipped it or before you flipped it? After you flipped it, okay. As a reduction potential, it's a negative 2.37. So since we flip it, it now becomes E with an oxidation, and that's a positive 2.37 voltage. The chromium one is normal because it's still being reduced, so we just look for it regular here, +3 to +2. What is its value? So for the chromium one, it's going to be a negative what?
Do we have to double it? Yeah. Wait,
No,
you don't. Here,
remember, this one is an intensive property, so even though we multiply, we do not change the E cell value. So that's a good point to make right there. Yes, you would not want to multiply the E cell because, or the standard reduction potential, since the magnitude does not change, the amount does not actually change the value of the amount of electrons being pushed along the wire or pulled along the wire. So we end up with an overall value of 1.87 voltage, which is positive and therefore meets the criteria of being a galvanic or voltaic cell. So now what I'd like you to do is I'd like you to try number 2. Number 2 is a little bit more complicated because you do have to throw in the waters and the hydrogen for the dichromate, particularly that half reaction there. Okay, so that one's kind of a long one. You do have an exchange of 6 electrons over here on the left-hand side. Easy to miss because you have to double the chromiums, and then you have to count that as, plus 6 on that side. And then over here on the right, you have to double the fluorides, and then you have to multiply the whole thing by 3 so that you get 6 electrons to cancel. Question?
Multiply that here on the right side. Should we go to the CO2?
Oh, yes, it should. You're right. I didn't multiply this, did I? This should be a 3Cl2. This should be a 3Cl.
Yeah, that one's 6.
6, correct. 2 times 3 is 6. You're right. You should drink more coffee. All right. So then this needs to be a 6. This needs to be a 3. Let's make sure we have it right now. Do you agree with it now? Good? Yes? No? Now, the chromium one, you flip. Looking at the standard reduction potentials, it becomes negative 133. This is probably not the combination you want to stick in your battery. Anybody want to suggest a reason why?
Because it's very, very low E cell.
It's a very low voltage, yes. 0.03 is not going to give you lots of power. Probably don't want to make this one your battery, no. Here is our voltage, here is our balanced reaction. On this one, not as difficult because why?
There's only just those no oxygen or stuff.
No oxygen or hydrogen or waters to worry about here, so that one makes it easier. All right, now moving on to some more stuff. Quick little review here. Description of the galvanic cell. Remember, in your textbook, the references, they call it a voltaic cell a lot, but galvanic, voltaic, they mean the same thing. They mean they're spontaneously run. They do not need a power source. When it's spontaneous, that means when you add the 2 half reactions together, their standard reduction potentials. Flip the one, get the standard oxidation potential, add them together and you get a positive cell potential, then it's going to run spontaneously. You don't need to do anything to it. It will just work. The electrons will flow. You attach the wire, you attach the 2 together, you attach the salt bridge, you will get power running through the system. You could attach a voltmeter, and then you can measure the actual voltage going across the wire. So, always spontaneous for a galvanic voltaic cell, always a positive E cell. Now for the diagonal rule, and this one really only works if you're using the table that has them arranged by their standard reduction potential values. So over here, the actual numerical arrangement ones, not in alphabetical order, the diagonal rule only works if you are looking at it arranged like this. This is the way the table that you have in your notes is arranged. But the basic rule is that any species on the left of a given half reaction will react spontaneously with the species that appears on the right when it's below it. So what am I saying here? I'm saying that the fluorine right here will react spontaneously with this silver, that's a silver ion. So it's like diagonal. It will react with silver ion spontaneously. Because if you think about it, all I would be doing is taking this value and flipping it, adding them together, I'm still going to get a positive E cell. Does that make sense? So the F will also, if you diagonal down here, react spontaneously with cobalt 2 there. All you would do is you would take this and flip it, add it to the fluorine's standard reduction potential, and you still have a positive E cell. So as long as it's down below, less than it, it's going to be able to flip and still add up to being a positive cell potential, yes. And it will still be spontaneous and fitting the description of a galvanic or voltaic cell. That would be for the fluorine. Yes, fluorine will react with anything. Over here on the right, it'll react with water. It will react with the Ce3+. Down the table, it will react with anything. As a matter of fact, with the lithium at the very bottom, that one produces the highest cell potential because you have 2.87 plus the 3.05 once you flip that one. That's like 5 volts. That's a pretty high voltage. Harnessing, though, fluorine as a gas in a closed chamber is kind of difficult to do, but that's why we don't hear about all of these fluorine batteries out there. You could still use this method for something in the middle. Like, for instance, I'm looking at this cobalt 3, it will react with water, but it will not react up with the silver, it will not react up with the fluoride. Because if you were to flip those, these now become higher negatives, and your E cell comes out to be a negative value, and it won't be spontaneous anymore. Does that make sense? A couple of things to review before we get into some of the other equations. Things for a complete description of a galvanic cell. Must have a positive cell potential. Must have balanced reaction, and we balance it based off of what? This is where everybody messes up on the test too. They see a redox reaction and they start balancing, but what do they forget to do? Balance it based off the electron number. So positive E cell must balance the reaction based off the electrons. Don't just do coefficients. Everybody always misses that question on the test because they just go right to balancing it like it's normal balancing equation. Redox, you always have to break it down. You have to look at the electron count. You have to balance the charges, all that stuff. So don't miss the balancing question. And our electrons always flow from what to what? Anode to cathode. It's always a flow from the anode to the cathode. And last but not least, how do we designate our anode? What do we know is going to be in the anode of the cell? So we say anox, to remember that the oxidation half reaction goes in the anode, and what do we say for the cathode? Red cat. Red cat means that the reduction half reaction is going to take place in the cathode. So anox, red cat, these are good ways to remember which half reaction is taking place in which part of the cell. New equation. Some new variables here. Free energy and cell potential. So gives free energy, tells us, about being thermodynamically favored if you need outside energy source in order for the reaction to occur, or does it have enough free energy on its own where it doesn't need anything to run the reaction. For our galvanic voltaic cells, they would fall under the spontaneous part where they wouldn't need any outside energy in order to run. They could just run on their own. Now the delta G standard, still the same thing, standard conditions. The new variable up here for the N, still moles. We use N for moles a lot. However, it's very specific type of moles. We're talking about the number of moles of electrons from the balanced reaction. So in our previous number 3 there with the gold and the bromine, that galvanic cell had an exchange of how many electrons? It was 6, right? It was 6 electrons. So that number, if we were looking at that particular reaction, we would put a 6 in for the moles of electrons there. So the amount of electrons being exchanged are going to be considered to be the moles of the electrons for the reaction. Now Faraday's constant is on, this is on your formula sheet, by the way. You don't have to memorize that number. That's on the formula sheet. Faraday's constant is like a conversion factor 2. I know we just plug it in here and we can solve in the equation, but consider Faraday's constant like this: coulombs over 1 mole of electrons. So it is just like a conversion factor as density is, you know, where you would do grams over the volume or the mass over the volume, and you could use it and flip it and put it in a T-chart. Same thing here for Faraday's constant. 1 mole of electrons equals 96,485 coulombs. And the voltage is a measure of joules per coulomb. Joules over coulomb. Another question is, does anybody know what a coulomb is?
It's a unit.
It is a unit. What's the unit that what does it measure?
Columbus cloud.
Not the Columbus cloud, no. What is coulomb? Yes, coulomb is a measure of charge. Now, when you were, taught the idea of the ionic bond, remember sodium gives up an electron to chlorine. Sodium becomes +1, chlorine becomes -1, and now they have opposite charges, so they attract to one another, right? The positive and negative attraction of the charges is called a coulombic attraction. So when you're thinking or hear the word coulombs, you should think of it as a measurement of charge. We know electrons have negative charges. So the coulomb measurement, you'll probably see it in physics as well, because then when you get to the electrical circuits, you'll see this as a unit there too. It happens to be a measure of charge. And we're going to be using that word again in Unit 7. So I wanted you to get used to the idea of when you see that word, think of, we're talking about positives and negatives there. In this case, because we're really focusing in on the electron flow, we're looking at the negative charges. And the moles of electrons equaling the negative charges involved there. Although it can apply to the positives as well. Now, if we're going to be canceling our units correctly, because we know delta G is supposed to be in what? Kilojoules per mole or kilojoules. It can be depending on how they cancel, but for the most part, yes, kilojoules per mole. But up here, we would look at, we have our negative out front here, moles of electron, and we would have our 96,485 coulombs over 1 mole of electron. And then our E cell is in volts, right? So volts would be the joules over the coulombs, right? That would give us our delta G, like so. So if we're canceling, the moles of electrons, they cancel. The coulombs are going to cancel. So we end up with this joule value, and we would need to take that joule value and do what with it? So joules to kilojoules, yes, divide by 1,000. There we go. This formula is also on the formula sheet, so you don't have to memorize it. Along with Faraday's constant is on the formula sheet. You don't have to memorize that either. It's in the electrochemistry section at the bottom. All right, so one thing to note, because we're now comparing cell potential and relating cell potential to delta G, we can tell something about our particular cell if we know, the E cell, cell potential, or if we know delta G about it. If delta G is negative, we know that E cell must be positive, and we know that it's a galvanic cell or voltaic cell. And we know it's spontaneous. If the E cell is negative, we know delta G must be positive, and it's not spontaneous. Okay? In order to get a non-spontaneous cell to run, you have to provide power for it, and that's later on in the unit. That's called electrolysis. And we would add power to make it run in the other direction. Cell potential and concentration. This particular set of exercises, you're going to be referring back to Le Chatelier's principle. And you're going to be looking at it qualitatively. There is a quantitative way to ascertain this information too. It's using the Nernst equation. However, now on the AP exam, they don't really require that you know the Nernst equation. You can derive the Nernst equation from the other two that are on the formula sheet, so if you do need to use it possibly. But up here in these examples, you should be able to kind of tell based on the flow of electrons and the direction of the reaction. So, for instance, normal standard conditions, everything would be 1 molar. So this would be 1 molar. This one would be 1 molar if we were just at standard conditions. However, first example, it has now been changed. The aluminum is no longer 1 molar. What is the aluminum now? 1.5 molar. Good. So we've upped its concentration. When you add in something to a side of a reaction, what happens with Le Chatelier's principle? We've disturbed the equilibrium. It's going to go the other direction. It's going to proceed, in this case, left towards the reactants, right? But what does that do here in terms of our E cell? Voltage occurs because the electrons are flowing from the anode to the cathode, right? So if we added in some of the stuff in the cathode here, and it's now pushing, the other direction. So the new non-standard E cell is going to be less than the standard E cell. So you would write it like this: E cell without the little degree symbol is now going to be less than our standard E cell. The standard E cell is when they're both 1 molar and it's flowing normally and creating the voltage. But since we've now altered it, it's going to backtrack a little bit towards the reactants. And our E cell, new non-standard E cell, is going to decrease in comparison to the standard E cell. Does everybody understand what I'm saying? On there. Good. Since this is being upped, we're upping the reactant this time, leaving our product as normal standard conditions. Now it's going to push towards the products, and therefore should be creating more electron flow. More electron flow means E cell, non-standard, should be greater than the standard E cell. What do we think here? If we've changed both of them now to 1.5 molar, they're both at non-standard conditions, but we've upped the reactant ion, upped the product ion, so it's kind of an equal cancel out deal where we're pushing some of the electrons backwards, but we're also increasing the flow forward, right? So no change would occur to the voltage. Exactly. So non-standard E cell should equal the standard E cell. Does that make sense?
Yes.
So we're equally creating a point where the pushing and the pulling now have equally been upped, and therefore the voltage should not overall change. Now for the Nernst equation. I'm just going to have you make note of it. There's like one problem in the problem set. It's one of those tutorial ones that you can work through the hints if you need to. But where you do plug in some numbers. And the Nernst equation is derived from the non-standard delta G equation that we looked at before. And applying it to cell potential here. It's virtually close, yes. We're still using R as the ideal gas constant, the 8.314 joule version of the ideal gas constant. Temperature is still in Kelvin. You have a couple new things here. You still have those moles of electrons on the bottom. That N is for the moles of electrons. And then you have Faraday's constant in here as well.
This is not given on the phone.
This is not given on the formula sheet. You can derive it from the equilibrium ones. The equilibrium ones are on the sheet. I'm going to show you how to derive it in just a second. And you would find Q, because Q would be the thing really mainly being altered. They can alter temperature too, but a lot of times these problems you're really looking at the concentrations or the partial pressures of the gases changing. And you saw that probably in your delta G problem set as well, that it really didn't change the temperature all that much. It was more about changing the concentrations or the pressures that were used in these equations. But this is just really applying to the non-standard conditions where you're not using 1 molar solutions or 1 atmosphere partial pressures if there's gases involved. And you would plug in your information. You would still look up your standard reduction potentials, flip the 1 and get your standard E cell because you need that for this part of the equation. You would get that part right there off of the table. And then you could plug in the rest of the information provided. Now, at 25 degrees Celsius, they give you this other version. So really, the RT and the F have been calculated here for you. Because at standard conditions, 298K, you end up with this 0.0592 number. Like I said, a lot of times what you'll see with these galvanic cells and changing them, they're not really changing the temperature all that much. They're really more focusing on the concentrations. And the Q is what is going to be different there, the Q. And they changed it to a log of Q. Don't ask me mathematically how that works out. From natural log to log, apparently it works. Yes?
Or like, you just reminded me of the quiz when you said absence of substance. On like the quiz last class, they said calculate delta T standard at certain Celsius that's not 25 degrees, and it's kind of confusing because they were at standard conditions.
Yes, in those particular cases, though, that one you're using the delta S and the delta H to find the delta G. And we're assuming that delta H and delta S are not changing with the temperature, and those actual values were calculated from the 298 version, yes. It does get a little confusing. Now we assume that as we change the temperature, those delta H and delta S values do not change. They do slightly change, but for our calculations, that's what we're going with. All right, so now we can change it over into the equilibrium form because E cell would be 0, the non-standard E cell. Q would equal K. So basically Q becomes K here. And you move the things over, you drop the negative sign, and you rearrange your variables. And now you have the equilibrium ones. However, like I said, this one you can derive from formulas on your formula sheet. And on the next slide, I'm going to show you how to do that. But go ahead and write them down so you have them to look at. But remember, at equilibrium, there is no flow of electrons. So E cell 0, you have a dead battery. It's not working. The two components have the same free energy, the anode and the cathode. So no voltage, no flow of electrons across the wire. So when it says that in a free response question where it says the battery's dead, that's key vocabulary for it. You're at equilibrium. E cell is 0. Delta G is 0. Okay?
Wait, if it's negative, the battery is negative.
If what's negative?
So,
If E cell is negative, you don't have a spontaneous galvanic cell.
and the battery.
No, it's just, it doesn't work at all. Yeah, it's not going to occur. Yes. Now, you would start out with a positive E cell, but eventually after the components run out and the electrons have flowed in their direction and you run out of juice, basically, it will eventually go dead. What could be due to the salt bridge components running out, or the solutions, or the electrodes. Yes, it could be a number of things that eventually get it to that equilibrium where there's no more flow of electrons. And that's what the recharging process does if you have a rechargeable battery. It actually, the power source has the electrons flow in the opposite direction, kind of resetting some of those original components so that now you are not at equilibrium. And when you're not at equilibrium, now you can have a positive cell potential and you can have some voltage. So this is the one that's on your notes here, but these two right here are the ones on your formula sheet. You'll see this one. We know this one from delta G. We know this one from electronout. But how can we derive this one from those two?
Substitute.
You just make them equal to each other, and that's how you can derive the Nernst equation. And that's the expectation, that the College Board expects, that you would be able to derive it and use the Nernst equation there if need be. Because, yes, you could just set them equal to each other. And then all you would have to do is do what? Divide this one, right? And now we have that equation, right? Because the negatives would cancel out. This becomes positive, that becomes positive. And you have now derived the equilibrium version of the Nernst equation. And you can always resubstitute it back to the non-standard version. Because remember, in this one, the E cell was 0. The non-standard E cell was 0. So you can always substitute that back in and work backwards to the non-standard equation as well. And, it's good bit. These two are on your formula sheet. So at any time, you can use them to derive the Nernst. So the E red for this one is, what's that? That's what I'm getting, yes. Okay, just checking. And for the iron, that one correct? Now, obviously, in order to create a positive E cell, which one do you need to flip? Zinc needs to flip. So this is now going to become the oxidation version. And it's going to be positive, and we're going to also flip it, so this will be Zn. Correct?
Correct.
And our overall cell potential, B cell now is good. And balancing our overall reaction, what's nice and convenient for us this time? No oxygen, no hydrogen, but
And it's already easy.
we already have an equal amount of electrons, so we can just cancel and add them together. And I know that the zinc is the solid since it's written as zinc metal, and the ones that are ions are going to be aqueous. So you can write them as such. Like so. Now calculating delta G, which equation should you start with? Delta G equals negative NF B cell, yes. So our N value is what? How many moles of electrons got exchanged? 2 moles. Faraday's constant. And the E cell. Remember, this is joules per coulomb. So we can cancel once again. You don't have to do this each time. I'm just trying to demonstrate one more time how we end up with joules. And joules for this, how many significant figures? What's our measured value that we would base it off of here?
E cell.
The E cell. And how many digits does the E cell have? Has 2. So we would only keep 2. All right, so give me the calculator answer. Yes?
Yeah.
And it's negative, right?
Yeah.
And so to round this, we keep our 6. We round this up to a 2. Everything else becomes a filler 0. And then, yes, we would divide by 1,000. It ends up being negative 262 kilojoules. That makes sense, though, because the E cell is positive. So the delta G should be negative, correct? The E cell is positive. Delta G should be negative according to our spontaneity rule, where it's spontaneous. If delta G is negative, E cell is positive. Now, we need to find K. So which equation would we use here?
Well, you can use either the ones E cell or you can use delta G ones.
You could use the E cell one, the Nernst, or you could use the delta G one, which is on your formula sheet. Doesn't matter. I'm going to use the delta G one since we just calculated delta G.
Trying to use the other one.
And this one ends up being what? Negative 0.08314, because we have it in kilojoules. And T is 25 degrees, so 298K, and then lnK. And remember to e to the x to undo the natural log there. And what do we get for our K value? Times 10 to the 10. Now, does that K value make sense?
Oh,
Yes. It does make sense. If we have a positive cell potential, a negative delta H, which way should the reaction be running? Towards the product, towards completion, right? If we're thinking about our equilibrium as products over reactants like such, we should be creating a lot of product. A lot of product. Yes, very little of the reactant. So lots of products being created. That K value does match our other two, negative delta G and our positive cell potential.
E cell's pretty big.
Yes, but still running in a spontaneous forward reaction where we're creating products, no backtracking really occurring here, so forth. Yes. All right, let's have a little discussion about batteries. Battery is a galvanic cell, or more commonly a group of galvanic cells connected in a series. Because as you see, that particular one only produced 0.32 voltage, so that's not a lot of volts. However, the D batteries that I have over here in the classroom, those ones are only 1.5 volts each. And they're kind of big. And then, of course, the ones that you use in your smoke detectors, the 9 volts, they have the little, different connectors at the top. Those ones, 9 volts, it has to be a series of a lot of higher stuff. It's probably why they're a little bit more expensive to buy. We're going to actually be using the 9 volts next week when we create our electrolytic cell, because we're going to be running it backwards, so we need the power source. And we'll be using the 9-volt batteries to do that. But inside your battery, there's going to be not just one cell, but multiple cells connected to produce that voltage needed. And then, of course, depending on the electronic device that needs the power source, you would use the current type of battery to power it. Now, batteries, you don't want to just crack open and check out, because not only are some of the chemical components in it and the half reactions are necessarily things you want to touch, but most of your batteries and most of the one of the half reactions at least will probably need to have an acidic environment in order to run, so that the battery acid in there isn't something you want to mess with either. Specifically in car batteries, they use some serious sulfuric acid in those. The car batteries are these lead storage batteries, and this is the overall generalized reaction for it. The thing that's kind of interesting in this overall generalized reaction is that the lead is being oxidized and it's being reduced, all in the same field. If you look here at your overall reaction, you're going to see that lead is going to go from being 0 over here to the +2, and then you also have reactant where lead is at +4, also going to the +2. So it's kind of interesting, the lead storage batteries, how they run. And looking up here, is 0, this is +4, and here the lead is +2. So you have one being oxidized, you have one being reduced in the same reaction. And then once you turn on your car and you have your gasoline running the engine, that fuel source allows to get the battery to recharge and run backwards, basically the power source, getting it to reset. And these guys you're supposed to last about like 10 years. No, this one's not balanced, but the only really thing that's, I'm trying to point out here is that in this particular case, the lead is being oxidized and reduced. It is the major component here.
That's weird.
Yes, it's in an aqueous solution. It's this big, like, rectangular thing in your car, if you've never seen it be replaced or anything. Now, the other thing about the lead batteries is we don't want to just throw them away, right?
That would be terrible.
Why would that be terrible?
Because lead is toxic.
Lead
It
is
would get
toxic.
in the environment and kill things.
Yes, we wouldn't want the lead to be dumped in a landfill, and then it could be, with the rain and everything, seep down into the water table. Lead's very toxic, poisonous. It causes brain damage. Yes, not okay. Not to mention the very concentrated sulfuric acid in there too that we wouldn't want going into the groundwater either. But environmentally, when you get they last a while, but you occasionally have to get your battery replaced, and you have to take it. Actually, the automotive places usually have a place to take them so they get disposed of properly. But you would never want to just throw it away. And most of the time with batteries too, you shouldn't really just throw them away. There are recycling places like at Home Depot and Lowe's and stuff where you can usually drop them off.
Well, if it's exposed to oxygen, but it's
Well, if it's exposed to oxygen, I know that, that could cause some corrosion, and it would probably, yes, if it's not, if it gets oxidized with the air, then it's drying up. Yeah, and you're producing oxides, and it's not necessarily you're gonna run out of your components, and then it'll die faster. Yeah. All right, corrosion. Corrosion, spontaneous oxidation of metals. This is a big problem. And in this particular case, we're showing rusting here. Rusting is the one involving iron. But any metal can oxidize, and it forms a type of, rust isn't the correct word, but it forms an oxide. And therefore, the rust, though, really, that word is pertaining mainly to iron, and it turns that, reddish-brown color and all of that. Although, the copper in the Statue of Liberty, it's, oxidizes and it turns green. You've probably seen that one before. But the problem is, we're looking here at the E-ox here for the oxidation of the water when it's in presence of oxygen is plus the iron. Guess what? This adds up to being a very positive E cell. So it's going to spontaneously occur, whether we want it to or not. It's not nice that our beautiful metals and things end up the iron will rust and other things will corrode. So we have to do a lot of preventative measures in order to keep these things from oxidizing. Why? Because most of these metals, like iron is used in steel, alloys. It's a structural component of lots of buildings. Lots of structures are made from steel, and we wouldn't want, the breakdown of those structural materials. We don't want the buildings falling down on us. Or, other things like cars and boats and things that are structurally made of these metals. So this is big business here, preventing corrosion. And methods of how we can prevent corrosion. No, aluminum actually, I think even.
Wait for the aluminum oxide, because that actually protects it.
Yes, well that wouldn't further break down. Exactly. What about what?
It's clearing.
You have to look at the reduction potentials to see if it will oxidize with the air and the water. So here is a diagram. This one's out of your textbook, but this is kind of showing you. Also, with the, if you have salt, like if you live near the beach, there's a lot of salt in the air and the atmosphere. Because the dissolved salt has charges, it conducts the electrons faster. So it actually speeds up the process on you.
It's a salt bridge.
It pretty much, yes, makes them flow faster. So if I had a bicycle here in Northern Virginia and a bicycle in Virginia Beach, and I left them out in the same conditions over the same period of time, which one would rust faster? The Virginia Beach one, because there's lots of salt in the air and the atmosphere, and because the presence of those ions, if it rains, you get the water on it, get the ability to conduct the electrons faster. And as you can see here, like the water drop here, you have your anode area where the iron is oxidizing. Electrons are flowing over here through the rest of the iron. But your iron 2 ions, flow through the water. They also come over here and deposit. So it becomes a much more speedy process when you have salt in there. You're welcome to check this out in your textbook. Okay? But the idea, this also occurs, with like zinc and other metals too, but this is specifically for rusting. But we have ways to prevent corrosion. Most of the time, they're coated or painted with things that are not going to be corrosive, or they put like zinc in there, galvanizing, because zinc is cheaper. It's kind of considered to be a sacrificial metal. where the oxidation will occur on the zinc and not the actual structural metal like the iron. So that's what the galvanizing process, they add zinc in there so that the zinc coating will be the one that corrodes. And of course, especially for like our Navy ships out there and other boats, they're just constantly painting them. They gotta keep constantly slapping on the coating because they don't want it to obviously corrode or rust because these things are expensive. Alloying with metals form these oxide coats like she was saying about the aluminum oxide. Once it forms the oxide, it doesn't really corrode anymore. So it forms like a thin layer outside of an oxide, protecting the metal as well. The cathodic protection is really interesting method. Catch large pieces of the active metals, like they'll put a magnesium strip on the bottom of the boat, magnesium strips around. So it's like the sacrificial metal. It gets oxidized, leaving the other stuff, the less reactive stuff, alone. But that means then they have to replace those from time to time. Like I said, with the Navy ships, they're constantly repainting. There's a person that does that. That's their job. They're just out there painting the ship all the time, making sure, you know, we don't have oxidation of our metal ships. Any questions about that? Because corrosion, prevention of corrosion is big business. It's really important, and we want to make sure that, yes, the structural integrity of our buildings and structures stay intact. This one's showing how the zinc coating on top is protecting the iron below. Okay, so it's being oxidized on the top. That one's in your textbook as well. So the zinc coating is being the sacrificial metal and being oxidized and corroded first. So here's the cathodic protection. Protecting your pipes. If you have metal pipes, they usually will bury a magnesium big chunk under the ground there, acts as the sacrificial metal, so that the metal pipes aren't being corroded underneath the ground. So electrolysis, we're running the galvanic cell backwards, and we're able to do this because we're forcing it with a current. We're actually attaching it to a power source, a battery, and that's what we're going to do in the lab. We have our alligator clip, and we're going to be using 9-volt batteries, and these are our nice electrodes, a double sharpened pencil, because what's in the middle of our pencil here? Graphite, so that makes a very good inert electrode. That's one of your pre-lab questions too. Why would it be considered an inert electrode versus just a regular electrode? Because it doesn't do what? It's not part of the reaction. It's just a conduit. It's allowing the electrons to flow, right? So it's not really part of the reaction, but we have to use it for our reaction because everything in our reaction is going to be aqueous, and we're going to have it in solution. So we have to have something that can act as the electrode in order to make the electrons flow. But the power source here, okay, is going to make the cell go backwards. So we don't have to have that positive E cell, that positive cell potential. We're going to be reversing the anode and the cathode here. Still going to flow from the anode to the cathode. It's just the anode, what's in the anode and what's in the cathode produces a negative cell potential instead of a positive one. So we give it the power source to make the electrons flow. This is a very useful tool. Electrolysis is used in big business and industry in order to get substances like sodium metal. They make sodium metal by melting down sodium chloride salt, you know, the stuff we put on our food. They melt it down into a molten liquid phase. It's like lava, it's molten. But then they run power through it, which breaks apart the sodium and the chlorine. But what's nice about this is, what does chlorine come out as when it's by itself, an individual element? a gas. So the chlorine comes out as a gas. So what are we left with? Our solid there is now just sodium. So this is how they make sodium. And they do it for other things as well, because when you mine ores and things, they're not pure metals. And to extract the metals from the ores, they use electrolysis a lot in order to get it out and be able to find and manufacture the pure metals. And then there's, of course, electroplating. Electroplating is like putting a layer of a metal on top. And, you know, a thin layer of metal on top of another. Usually it's used for aesthetic purposes, to make things nice and shiny and pretty. A lot of times done in jewelry. They'll, you know, most jewelry isn't going to be pure solid gold or pure solid silver or anything like that. It's going to be plated, because then it makes it a whole lot cheaper, right? Okay? And sometimes they plate stuff with more resistant metals to the corrosion, because, you know, corrosion is such a big factor with our metals, and we don't want our structural things to corrode and prevent it. So electroplating, depositing a thin layer of a metal on top, can also be done there. Any questions? Now, one thing I also want to tell you about electrolysis, because this applies to the lab, is that when you have an aqueous solution, and this is in the lab so you can read about it, when you have an aqueous solution, you also have water in there, correct? Because it's been dissolved in water. Well, water has an oxidation and a reduction reaction as well. Now, if you look in the back of your books, there's a couple different versions of reducing water, and then you flip one, you can oxidize water to produce oxygen gas. So the problem is when it's an aqueous solution, sometimes the reaction for reducing the water or oxidizing the water is more favorable based off of its cell potential than the actual substance itself. So sometimes you might see at the anode, instead of, say, the metal oxidizing or the non-metal oxidizing, you might see water doing it instead. You have to look at the cell potentials to decide what's going to actually occur. That only occurs in aqueous solutions where the water, you have to take a look at the water reactions. This is also in your problem set, that's why I'm going over this. You have to look at the cell potentials to see which one's going to be more favorable and decide which one's going to occur at the anode and the cathode. And you'll be looking at that again on Tuesday, but it is in the problem set as well. So definitely take a look at those cell potentials, because water can be more favorable than the actual reaction itself. And you might get, you know, when the water gets reduced, you get like hydrogen gas and hydroxide ions out of it. And then when water is oxidized, you get oxygen gas and hydrogen ions out of it. So one becomes acidic, one becomes basic. But depending upon the cell potentials, comparing them to the actual substances in the reaction, see if water is going to be more favorable. Okay? All right, so the galvanic cell, this is just a diagram. We have our voltmeter at the top, the electrons flowing from the anode to the cathode. Okay? The anode, too, by the way, will be in the left side of your simulation lab, too. In the first couple of modules, it doesn't label it for you, although you really don't need to know that. But the left side is going to be the anode, the right side will be the cathode in your simulation. So normal galvanic cell, it's just spontaneously flowing from the anode to the cathode. It has a 1.1 volts here. However, if we're going to electrolyze this and make it an electrolytic cell, we now reverse them. So the copper side becomes the anode, the zinc side becomes the cathode. They reverse, and you're attaching a power source. So now it's going to run backwards. And this is kind of how our rechargeable batteries work, because we're attaching it to a power source and we're forcing it to go the other direction to kind of reset and give our batteries, you know, a reset in terms of solutions, electrodes, and so forth. And therefore, now it has more juice and can run spontaneously on its own. So the idea of this, attaching the battery, makes the electrons flow backwards. And you see, now they're reversed. The anode becomes the cathode here. The copper is now in the anode. And the zinc is now in the cathode. So once again, let's just look at it before. The zinc was the anode, the zinc was being oxidized, the copper was being reduced. But if we run it backwards, now it flips. And now the copper is going to be the anode being oxidized, and the zinc is now going to be in the cathode and being reduced. The stoichiometry of electrolysis. So we're going to answer a few questions, and then I'm going to have you can look at it this way, but I wouldn't write down all the words. I've set it up in a nice T-chart for you to show you how you would cancel everything. But let's go ahead and answer our questions. The questions like the amps are going to be what unit do we use to measure current? We're using amps or amperes. In amperes, 1 amp is 1 coulomb per second. If you remember, coulomb is a measure of charge. In this case, we're looking at the negative charge for the electrons here, but coulombs can also measure protons and positrons and other things that have charge. But here, we're looking at the electrons. So, amps is the first question here. We're looking to answer that one. Amps can be 1 coulomb per second. Okay? That's how we measure the current that's flowing through from the battery to the power source. Okay? And if you multiply amps times seconds, what are you going to get? Amps times seconds should give you the coulombs. Okay, so now we're answering the next question. Amps times seconds should give you the coulombs. Okay? Now, looking at that, you divide coulombs by the Faraday's constant. What are you going to get? You're going to get the moles of electrons. So that's the next question, getting the moles of electrons. And then once you have the moles of the electrons, you can find the moles of your metal or the substance you're trying to produce, which is what we call the analyte. So it could be a non-metal we're trying to produce too, but a lot of times electroplating is about metal. So the analyte is the substance we want. Okay? We're turning it into a solid or into a liquid or whatever we want. We want to pull it out of the solution. And then we can change that into the grams of the analyte. So it's measurable amount on a scale. Okay? You're going to do moles of electrons to the moles of the substance in the balanced reaction. And then you can do molar mass to get to the grams. Yes, exactly right. Now, I do want to pay attention to Faraday's constant. Wasn't discussed earlier, but like 1 Faraday is equivalent to 1 mole of electrons, but it's also equivalent to the 96,485 coulombs. So you might see the word Faraday like listed as a unit, but really what it's meaning is like if it's this many Faradays, it's this many moles of electrons, or this, times the coulombs, you could get the coulomb amount too if you wanted to use that. But most of the time, if you just see the word Faraday, like you've got 1.2 Faradays, they're saying you've got 1.2 moles of electrons. That's on your checklist. I just wanted you to, understand that wording. So if you see the word Faraday, it's really referring to the moles of electrons in there. Another little point to make. Sometimes it's phrased that way. But at the top of your paper where there's more space, you can write down the T-chart. I set it up for you so you can kind of see how it's going to go in one big flow. You're going to put your time, and they usually give you time in hours or minutes, of course, because they want you to do that extra conversion to seconds, right? In this case, our problems, we're going to be using hours to begin with, and so we need to change our hours to seconds. And we did this in one step where we did 60 times 60 to get that 3,600 seconds. So that idea of diagonal down, okay, going to the next thing. So we go to seconds, we diagonal down the seconds so we can get to coulombs. This is where the amp part of the equation gets inserted. That's the amp, okay, because amps are coulombs per seconds, right? Then this is where we use the Faraday's This is the Faraday part where we're going to be able to change it from coulombs to moles of electrons. And then here, we're going to be able to go from our balanced reaction. Balanced reaction, we can go from moles of electrons to our moles of the substance. And last but not least, once you have the moles of the substance, you can always use molar mass to change it to grams at the end. So does everybody kind of see the nice flow? It's going to go in one big long T-chart. And that way, you don't have to worry about like rounding in between. Rounding in between and getting a different value. So write out this one, across the top, and you can see where we're inserting the different points. We have, time to seconds, the hours to seconds. Using the amp conversion, we're doing seconds to coulombs. Using Faraday's conversion constant, we can go from coulombs to moles of electrons. Moles of electrons to moles of our actual substance, the analyte, and then moles to grams. So nice big setup. We're going to do a couple problems now and go ahead and calculate it real quick. Before you begin though, what should you do? Before you set up your T-chart. Yes, our half reaction here, and so we can figure out how many electrons are being transferred in the process. That's what we need to do here. So if we have the cobalt 2 in solution, this is in solution, right? And we're trying to electroplate. We want to get the cobalt solid. So in that process, what's going to be the transfer of electrons? We got to have 2 electrons being transferred. So now we know our moles of electrons. We can continue with our setup. Correct? So over here, this should be 1 hour. And we're going to do our 1 hour equals 3,600 seconds. Then we would do what? Our amp conversion here. So we have 1 second equals 15 what? Coulombs, right? Because it's 15 amps, so it's coulombs per second, so 15 coulombs per second, right? So this is that amp conversion part right here. That's where we're using it. Next comes what? What are we inserting next? Faraday's constant, so the 96,485 coulombs goes on the bottom. And now we have 1 mole of electrons. So this is our Faraday's part. Then what do we do? The balanced reaction now, so we have 2 moles of electrons going to 1 mole of CO, the solid, our analyte here. And last but not least, we need, so this is from the, reaction. We get this information from our reaction. And last but not least, we have 1 mole of cobalt equals how many grams? 58.93. Okay, so we calculate here, and we end up getting our grams that we'll be electroplating and depositing. Our final answer, I think, ends up being 16.49. Is that correct? So we're going to keep it at 16 and go with that. We're going to do HF from aqueous, HF with a +4 ion. So this is going to be an exchange of how many electrons? 4 electrons, and then we get our solid HF. 25 it is. Now we're going to do, this is actually, we're going to be using Ki in our lab too, so this one's kind of similar to, would be a similar problem here. We're going to be producing iodine, I2, from Ki. So how is that going to look? Well, we don't need to worry about the K. Why do we not need to worry about the K? Spectator, not a part of the reaction. But we're going to be starting with what, though? Because this Ki breaks up into I minus, which is AQ, right? And it's going to go to I2 solid. Now, what do we need to do here? Got to balance the I's first, okay? So that needs a 2 there. So it's a total of what? Flow of how many electrons? 2. So which side are we going to go with the electrons here? Right. Okay. So still, it's going to be a transfer of 2 electrons, but it's set up just a little bit different because we're going to be going from I minuses coming together, losing 2 electrons to become I2. Just as long as we're producing the solid, and it's all about the transfer of electrons that you need to know the moles of electrons, yes. So it doesn't matter, yes, if the process is oxidation or reduction, it just matters that you know the electron number of moles. Mm-hmm. Exactly, good question. It's a little interesting too because you're extracting it, you know, like I said, from the compound, from the ore there, and the chromium oxide ore would be there. That impure stuff they mined out of the ground, right? So we have to figure out the charge change so we know the electrons of the moles of electrons. So we're going to be extracting the Cr solid from our CrO3. What is that? This is going to be minus 2, so this is a total of -6. So this must be a plus 6 in that chromium in the chromium 6 oxide compound. So it's a matter of 6 electrons that need to be added in. So it's a matter of 6 moles of electrons here. And let's set this up, finish this out, and we'll be done with our electrochemistry notes. Yay, I know, everybody jumped for joy. Yes. You do not need to fully balance it, put the water in and all that stuff, no. We really just need to set it up so we know the moles of electrons. No, you wouldn't need to set it up and balance it. Unless they gave you both half reactions and everything to begin with, here you're really just looking for the moles of electrons. Good question, yes. So we end up with, what is our final number here? 4.9, right? Is that what you got? 266, right? We have 2 in our measured value for the time, 2 in our amps, so that's where we're going to go with 2 for each of these. Yes?